Welcome to the another lecture of electronic devices. In this lecture, we are going to learn diode models. So, in this lecture, we are covering three different models of diode. First one is the diode ideal model, second one is diode practical model, and third one complete diode model. As we know that it is a two-terminal device which permits only unidirectional conduction. So, diode conducts well in the forward direction and poorly in the reverse direction. So, if it acts as a perfect conductor with zero resistance or zero voltage drop across it, so when forward bias, and as a perfect insulator with an infinite resistance or with no current through it when it reverse bias. So diode is a two-terminal device which permits only unidirectional conduction. So as shown in this figure, we are having conduction in forward bias but no conduction in reverse bias. So we can see that if diode is conducted in forward bias, it works as a perfect insulator, perfect conductor, and when reverse bias, it works as a insulator. So according to this, we can model ideal diode characteristic using this particular diagram. In the forward bias, that is with zero resistance and zero voltage drop across it, and in reverse bias, that is infinite resistance or no current through it. The ideal diode acts as an automatic switch. The switch is closed when diode is forward biased and switch is open when diode is reverse biased. So this particular circuit shows this functioning as in forward bias Vf is 0 and in reverse bias IR is 0 ampere. So I of F can be calculated as V bias upon R limiting resistance. So according to this, we can draw this diagram. It is on x-axis on voltage across diode, on y-axis the current in diode, 0 to positive x direction denoting forward bias, 0 to negative x direction denoting reverse bias of the diode, 0 to positive y direction showing us the forward current, and 0 to negative y direction shows us reverse saturation current. Through this diagram, we can see that Vf is 0, so we are having If at different values of R. Similarly, in reverse direction, R is 0, but we are having VR that is equal to V bias. These two circuits we can draw the diode ideal characteristics. Next characteristics is practical diode model. So in practical diode model, we can add potential switching model. In this model, we are neglecting the dynamic resistance RD. So from this figure, we can see that a small voltage drop across a diode that is called Barre potential when it is in forward direction. So we are counting this particular forward voltage V of F while calculating the current through this circuit. So current through this circuit can be given by V bias minus Vf upon R limit. So according to this modified equation, we can draw again the ideal diode characteristic like this, in which V of F is denoted by 0.7 volt for silicon and 0.3 volt for germanium. Another model of diode is called complete diode model. In this complete diode model, we are counting Barre potential, dynamic resistance of the diode, and the internal resistance R dash. So the forward voltage is given by 0.7 plus IF RD dash, that is called forward VF. This particular equation we can calculate IF as V bias minus VF upon R limit plus RD dash. So according to this equation, again our characteristic curve changes as shown in this figure. So in this figure we can see that at 0.7 volt the slope due to low forward resistance increases rapidly, and in reverse bias we are having a parallel internal reverse resistance of the diode that is called R-R. So due to this resistance, our IV characteristic changes like small reverse current due to high reverse resistance. So to this particular models, we can calculate the current characteristics of a diode in a particular circuit. So in this example, we can calculate the diode resistance forward current according to these models. So this example says determine the forward voltage and forward current that is in forward bias condition for each of the diode model. Also find the voltage across the limiting resistor. In each case, assume RD dash equal to 10 ohm at the determined value of forward current. So we are having the value of resistance, that is 1.0 kilo ohm, VF, V bias reactive voltage 10 volt in the forward bias condition, and in reverse bias condition we are having R is 1 kilo ohm, V bias is 5 volt. So according to diode model, we can calculate the VR as in these three cases. So in ideal model, we are having VF is 0 volt, so IF is given by V bias upon R. So that is 10 volt upon 1K. So we can calculate IF equal to 10 milliampere. Similarly, VR is given by I of F into this particular resistance. So I of F we have calculated 10 milliampere, and the R limit for R resistance is 1K. VR is 10 volt in this particular circuit according to diode model. If we again calculate this VR limit to practical diode model, so in practical diode model we have VF equal to 0.7 volt. So in this particular circuit, VF is 0.7 volt. So IF across this resistance can be calculated as V bias minus VF upon R limit. So V bias is given by 10 volt minus 0.7 volt upon 1K. So IF is 9.3 milliampere. If we put this IF value in this particular equation, so VR limit is 9.3 volt. That is lower than ideal diode model according to this practical diode model across the VR. If we calculate using complete diode model, so I of F in this particular circuit can be calculated by using V of F, that is the summation of 0.7, that is barrier potential of the diode, plus I of F into RT dash, that is same as in this particular equation. So V of F is now 0.7 volt plus I of F RD dash. So as we are having R limit and RD dash barrier potential value, so we can have first I of F. So I of F is calculated as 9.21 milliampere. So through this particular value, we can calculate V of F by putting the value of I of F in this equation. So V of F is now 792 millivolt. So VR limit is now calculated as I of F into R limit. So that is 9.21 milliampere into 1K. That is 9.21 volt. So that is lower than from our both of previous cases. So these model calculations showing us that we are going towards exact calculation while using complete model. So in this particular slide, we have covered three different models of diode, that is ideal diode model, practical diode model, and complete diode model. Thank you.